Okay, thank you very much. Maybe I'll share my screen. So here's the alloys. So first of all, I'd like to say those of you that are material scientists, this talk has nothing to do with material science. And I hope I will take the time to explain what alloys may mean for me. So why we're interested in scientific computing and artificial intelligence, where there is all sorts of complex systems that we want to simulate. And then these complex systems, they span multiple scales. Their dynamics can be expensive to simulate or challenging to forecast. And then we're interested to design fast methods that reproduce the system dynamics. Of course, we are not the first to think about that. There's all sorts of great works that have been looking into developing methods for doing exactly these processes. And scientific computing actually has been a key enabler to do things like the ones that I will show you next. So there is all this talk about digital twins. So here's how scientific computing has been used in the past for digital twins in our lab. This is a device that is used to separate large cells from red blood cells. The idea is that you can use devices like this one, where you pass the blood through these posts. And then the idea is that larger particles, like circulating tumor cells, will be separated from smaller particles like red blood cells. So this is work with a group of Mehmet Toner, and here's a video of the device. They were developing this device, and they were very much interested to understand what were the workings. So we developed simulations of red blood cells. We were able to run up to 1 billion red blood cells using dissipative particle dynamics, running 1 trillion particles. The movie here you see is with only 350,000 red blood cells. You don't see the plasma. So by doing this forward type of simulations, we were able to examine certain scenario and then through surrogates actually to develop better posts that separate the particles from the smaller particles from the large ones. This is actually, just to let you know, this is a one-to-one device with the people, with what the people are having in the lab. So another things that we do is we are doing simulations of bubbly flows. We are developing computational methods so we can do tens of thousands of bubbles. I will not describe the numerics of that, but at the same time, you can do wavy flows. You can also do flows in microfluidic devices. And how do you use this? Well, you can study things like membraneless electrolyzers. You know about electrolyzers, taking H2O inside and then passing it through these electrodes and separate hydrogen from oxygen. The idea is that you remove the membrane from in between and you rely on fluid mechanics to separate the two species. The people we were collaborating with initially made a device that looked with these rectangular electrodes, and then you get bubbles to separate, but sometimes they also mix. So we did a lot of simulations. We developed a new device, like this, we call it the volcano, because it's kind of like pushes things in its own compartments. And then after that, the experimentalists, they go on and they develop these membraneless electrolyzers with the help of the simulations. There is also other things that you can do with computers, and you don't always need to rely on scientific computing to create the so-called digital twins. Here's a digital companion. The idea is that we had an engine, and the idea was that can I optimize the fuel injection rates of the engine? So what we did is we took a smaller engine, and then we complemented the smaller engine with with a computer, and then the computer will automate through multi-objective optimization algorithms the fuel injection rates. And then what we get out of this is we get a Pareto front of emissions and pulsation. The orange dot is where this thing was originally operating. So as I said, you have 8 valves that you are operating. So depending if you want to be in a low pulsation region, but you allow a lot of emissions, you operate like this. If you want to be in a region where you have low emissions, but then you can afford pulsation, you have a more uniform story. And again, all these things is that the machine here, the optimizer or the learner is together, still together with the machine and optimizes it as it goes along. So this is old works. This is 20 years old works. There's also another thing, which is 20 years old or so, at least for me. There is this concept of algorithmic twins. So what is it that I call an algorithmic twin? And perhaps you can start to see a little bit why eventually I'm going to be talking about alloys. Is you can take a classical algorithm like the singular value decomposition or PCA or POD, and then you can try to do dimensionality reduction. You get your data, you have a mean, you create a covariance, and then out of this covariance, you can keep from the largest eigenvalues and the respective eigenvectors, and that gives you dimensionality reduction. Now, of course, the question is that this is a linear type of operation. What if you don't like linear operations and you want to do something nonlinear? Then probably you'll have to go back and try to develop a nonlinear method of that, which is not clear how you generate a nonlinear method from this principle that we have here. Now, there's an alternative way that you can do this, and you can do this through autoencoders. The idea is that you are creating identity mapping between your data and the data itself, and in between you pass it through some kind of a linear neural network in this case. So you put these weights, and then here this network is a linear, again, linear neural network, so it amounts to matrix vector multiplies. People have shown a long time ago that this type of thing is equivalent to the PCA, and now you have a very interesting juxtaposition. From one side, you have these mathematical forms. In the other side, you have this architecture, if you like, and now it's very interesting that this architecture is kind of straightforward how you can make it nonlinear. You make it nonlinear by simply taking the weights here and making nonlinear activation functions instead of linear activation functions. And also you can decide to play with the architecture, add more networks. So in a sense, you're able to do similar things, but now you have a little bit more flexibility and a little bit of more degrees of freedom in order to go to the nonlinear world. So this is something we did about 20 years ago. I think we were the first to actually do deep neural networks for a scientific application. We were trying to reconstruct the near wall turbulent flow from information only at the wall. We were actually playing with neural networks to do that. At that time, a few layers didn't work, so we ended up adding layers until this thing works. So that's why I say this is one of the first applications of deep neural network scientific computing. And you can see if you want to do reconstruction, this was the original field. This is what a POD, a linear reconstruction, will give you. And by adding layers and nonlinearities, the neural nets are able to give you a much better reconstruction. We have been working in a lab in this composition between scientific and machine learning for quite some time. And there is here, this is a graph that shows you what I think has been a key difference over all these years. What you see here is the computational capacity of supercomputers. The orange curve is the top computer in the top 500. The yellow curve is the number 500. And I use this graph, and I also use two papers that I wrote. One that I wrote back in 1999 about machine learning algorithms for flow modeling and optimization. That was actually not possible to publish anywhere except at the CTR annual research briefs. And there's another paper that I wrote a few years ago that has received thousands of citations. For me, the difference between the two things is that back in 1997, when we were doing this machine learning work, it would take a year to train a neural network in the best supercomputer available. And now it will take less than a couple of minutes to do the same training. So this opens new horizons and new ideas of how to think about machine learning and scientific computing. Now, scientific computing and machine learning, or AI in general, for me are two distinct animals, and I would like to explain. So in scientific computing, we always had this quest for exactness. We're looking at numerical error of second order and so forth, fourth order, high order methods. Now in AI, you're looking into statistical inference. You're looking at expectations, you're looking at averages. This high degree of accuracy maybe is not even relevant. My understanding of AI also is that it is goal-oriented. You're trying to achieve something and you don't necessarily try to understand what happens. Of course, it's very useful to understand. That has been the core of scientific computing. And as I just showed you, the way that this type of methods have been formulated, you have mathematical forms from one hand, and then you have these architectures and heuristics and all sorts of flexibilities from the point of view of artificial intelligence. So here's the question: can you combine the best of both worlds? And the idea is the same way as you have in metals alloys, and where the union of the two metals is something that is better than each one of them. That's actually what I'm suggesting, and what other people have also been doing in trying to combine AI and scientific computing. I'd like to show you three examples of what I call alloys. One of them is learning the effective dynamics of complex systems for multi-scale modeling. I would like to show you a technique that I think puts the physics-informed neural networks in another perspective. I call it optimizing the discrete laws for inverse problems. And I will conclude with scientific multi-agent reinforcement learning for closures of, and for control and for closures of numerical methods. So let's go and let's start with this LED. The first idea is, can I use neural networks to predict the dynamics of complex systems? What you do is you have some data, you use a neural network, and then you do some kind of optimization. This allows you to create a neural network model. Here what you see is the element of an LSTM. And then, of course, the testing is, can you predict the dynamics on unseen data? So for data, I decided to use here data from the solution of the Kuramoto-Sivashinsky. We have this equation. It exhibits some kind of chaotic behavior depending on this parameter L tilde. This is an important point I would like to make. You can use your classical scientific computing, you can discretize it. And what I do now is I will be collecting some data from the Kuramoto-Sivashinsky. I'm going to be training my neural networks with this data, and I would like to see what kind of predictions the neural net will produce. And I have my numerical solution to test the predictions of my neural net. Now, as it turns out, the data we used initially, we started by using the full detailed simulation of the Kuramoto-Sivashinsky, and we were mapping it to recurrent neural networks with long short-term memory. And we found that when we were using the high-dimensional data, that means all the data in every spatial point of this 512 discretization, and all these minute time steps that we took, the recurrent neural networks with LSTMs were difficult to train. So we resorted to another technique, and that was to go back and do an SVD on our data, throw away the modes with the low energy, and instead to train our networks on low-dimensional, reduced order data. So here's what came up. So here's the forecasting on unseen data. So we have, this is now testing. And then again, I have trained on the short-term history. This is the part where I have trained my neural networks. And now what I want to see is if I'm able to advance in time. I'm using RNN LSTM. I'll make a comment about different architectures later. And now, right after I have done the training, I'm able to do a quite good prediction. Now, if I move again further in time, I'm doing okay. I'm still doing okay, but eventually you start to see that these RNN LSTMs, they start to have problems. Eventually, when I go to time 4 and time 5, I start to diverge. And once you start to diverge, the two systems will evolve completely differently. Just to show you also how sensitive the training is to the chaoticity of the system, consider the predictive capabilities that I have for L tilde is equal to 8 or L tilde is equal to 10. So on the top is kind of a less chaotic, if you like, case. On the bottom is a more chaotic case. And now you will observe that actually the LSTMs, they're able to stay longer with the solution for the less chaotic system, and then they seem to fail quite fast for quite chaotic systems. So we did all these observations, and then we actually decided that these RNN LSTMs are not very good for the prediction of chaotic systems, at least the long-term prediction of chaotic systems, except that one day one of my students comes, says, look, there is this magazine that says the machine learning has the amazing ability to predict chaos. And not only machine learning has the amazing ability to predict chaos, but also they were quoting our work as one of the evidence that machine learning can predict chaotic systems. So as you can see in these papers, actually, we cannot predict chaotic systems. And in this paper in particular on neural networks, we actually discussed the mapping between the algorithms and the data. And we see that if you have high dimensional data, techniques like reservoir nets are maybe better than RNN LSTMs. So what we learn is that you need to have a mapping between the data and the particular algorithm that you are using. Unfortunately, this mapping at the moment is based on heuristics and on experience. But nevertheless, I maintain that by neural networks alone, you cannot predict chaotic systems for long times. Now, is this the end? Is there any use out of this? Lessons that we have learned? So we thought that these neural networks are interesting reduced order models. So is there a way to combine large-scale simulations and reduced order models? So here is the idea of the alloys. And the basis of our work actually is attributed to the pioneer work of Kevrekidis, that he came up with this equation-free framework. And what Yannis said, what if I do some kind of like, have some few steps in a large-scale simulation, I collect some data from this large-scale simulation, and then I use an encoder to get into a latent space, and then advance through some kind of a numerical integration in the latent space. Well, the complication with this technique of, one of the complications of this technique of equation-free is how do you go from low-dimensional spaces back out to high-dimensional spaces. And I know I was looking at this technique for about 20 years since Yannis first introduced it. And at the same time, I had these autoencoders, and then it just occurred to me a few years back that the two can be combined. So you can use actually encoders, decoders to create a latent space. And then whenever it is time to go back out to the full system to recalibrate your data, you can use the decoder to do this. So it's an iterative process between large-scale simulation, reduced order models. Machine learning helps you to exchange information between the two. And now this is how the algorithm works. And of course, the key thing is what is the ratio of the two times? How much time do you spend in the micro scale versus in the macro scale? So now let's look at Kuramoto-Sivashinsky again. Now I will show you results of applying now not anymore PCA, but applying variational autoencoders to find out the evolution of the latent space. And the interesting thing that we found actually is that previous work had suggested the effective dynamics of the Kuramoto-Sivashinsky lie on an 8-dimensional manifold, but then learning a propagator of these dynamics has been difficult. This is works that are about 30 years old or so. So now when we actually looked at the autoencoders, we actually found it surprising that if you're looking at the mean square error, when you found this latent dimension of 8, which is what the theory here has predicted, there is some kind of saturation of the autoencoders. And then you can see by comparison the PCA that we were using earlier, you have to go to about 20 modes to get this number 8. Now, what we did is next to do this LED framework. Now we stay here only in the latent space. This is dynamics only in the latent space. We do an extreme case where we don't go back out. We only go back out in order to plot our results. And then when you do that, when you, instead of evolving the system in the full space, you evolve it in the latent space. In the latent space, you get something that is unrecognizable. In the full space, you get something actually that looks reasonable, but not exact. And what is interesting is that you get good results when you're looking at the phase space. The phase space of the velocity gradient and the second derivative of the velocity, they seem to behave very well. And what we find is that we have a reasonable speed up, about 2 orders of magnitude, by playing this particular game. Now, the next thing is, of course, like every machine learning person, let's do the cylinder. So we did the cylinder, Reynolds number of 100. And what you find is you have small errors. And what was also very interesting is that even when you look at the drag coefficient, the bottom right over here, you find out that with only 2 degrees of freedom, you are able to get an error in the drag coefficient of about 4%. So a lot of people have done the cylinder, and usually machine learning people, when they do the cylinder at Reynolds number of 100, they declare victory and say turbulence is solved. I think the natural question is, how about Reynolds number of 1,000? So we asked Reynolds number of 1,000 to our method, and we fail. We fail in the sense that we are not able to have the same error. We have an error of about 20%, which is, in my opinion, not so good. The predictions they made look reasonable, but the interesting thing that we found is that if you just blindly take data, dump it into a machine learning thing and hope for the best, that you're not going to get a solution. And that's actually, for me, a hopeful message, because now what happens is if you look at where you make the largest error, you make the largest error near the cylinder. And that's actually a good thing, because that tells you that you need to capture the vorticity production through your autoencoders and the mapping that you do to the latent space. So we're doing actually now work where we're developing cleverer autoencoders that are more informed from the physics of the flow. The results, they look better, but this is ongoing work, and I would like to leave it at that. At the same time, I would like to stress that from my experience with machine learning, I think there is a lot of overexcitement, and sometimes we need to introduce benchmarks. So I would like to suggest as benchmark this flow behind the cylinder. There is a particular flow that is quite interesting, has some interesting analytical solutions for early times. That's the flow past an impulsively started cylinder. So what you will see is the flow past an impulsively started cylinder with 25,000, 50,000, and 100,000 Reynolds number, 2D, but resolving all possible scales. This case of the 100,000 has billions of computational elements. The structures that you get are quite striking about what flows may look at these Reynolds numbers. And I think that machine learning is quite challenged by being able to capture such details. I'm not sure we should even try to use machine learning to capture these details, but when we decide to capture some kind of average quantities, I will be curious to know what should be the average quantities we should be capturing in these flows. And just to show you that the technology that goes behind these things involves all sorts of wavelet adapted grids, extreme resolutions, and I think this is something that we still need to curate. You can find more papers. There is extensions of this thing to molecular simulations of the LED, but I would like to move to a second example of combining scientific computing and neural networks. So there's a lot of excitement about learning with neural networks, about learning without neural networks. Let me explain what I mean by that. So there is neural networks for PDEs, and there is the so-called PINs that people, what they do is they say, okay, I have a PDE, I have some boundary conditions, I take as an input to my neural networks X and T, and I have some weights theta. Basically, it's a nonlinear parameterization of the solution. How do you find out what are the weights of this nonlinear parameterization? By minimizing for the solution itself. It's an interesting idea. Now, the thing which I personally like about PINs is this idea that you can actually take data and add them as part of your minimization, so you have a compact form of the cost function, and then you can have your unknown solution, you're solving the equation, putting in the boundary conditions, any other constraint you have, and of course the data. I appreciate that there is a lot of complaints that this problem may not be well posed, and I totally agree with that. Nevertheless, I think the idea is interesting. Now, I would like to suggest an alternative idea, and the alternative idea is that usually we have this continuous problem, f of u, and here's the boundary conditions. But when we do scientific computing, we often discretize this problem. And so instead of using neural networks to write this cost function, what if we just take the discrete form of the equations and write it as a minimization problem? This is not a new idea, it's an old idea. The new thing is that you are copying from PINs the idea of embedding the data in here. And so you can do loss function, you can actually solve inverse problems. Now you're solving them on a grid. In this particular case, I'm using a grid to discretize my equation. The advantage is that you have a consistent discretization, that you take things, for example, locality of the solution into account, and so on. So with neural nets, sometimes you don't have that. So again, the idea is extremely simple. You just take the discrete version of your solution, you add your boundary conditions, and then you run a minimization. Now, let's compare the two methods. So here is the PINs. The solution is a neural network. You have the solution everywhere, and here is ODIL, what I call ODIL, where the solution, you get it on grid points. And of course, if you want the solution between the grid points or between data that happen to be between grid points and your place where you discretize, you can of course interpolate, but we'll leave it at that. Now, if you solve the wave equation, the PINs with 700 parameters, they give you a solution like that. The ODIL with a 25 by 25 grid, it gives you that. The reference solution looks like this, but now I want you to pay attention to two things. The error, first of all, for the PINs, it depends on the initialization that you do. You can get it to converge in this particular case. It's not always the case. But the thing that is quite striking is that basically by doing this discrete version, you can get things where if you use LBFGS, you find that it's 100 times faster than PINs. But now, by doing these discrete versions, you can use Newton, and you can be hundreds of thousands times faster than PINs. Solutions with this ODIL. So here I'm inferring the nonlinear flux. I have imposed the final solution and the initial solution. The unknown here is a neural network. So this ODIL seems to work quite well. We are doing other things of developing the conductivity from having different temperatures. So the temperatures are given to me as measurements here. Can you infer the K of U? What I find, it's actually, here is what PINs do. Here is actually a multi-resolution method that I will talk in a second. We have in ODIL, that's what it does. And the conductivity, more or less, all of them get the same thing. There are some issues here with the PINs, but that's just to show you what we can do. We can also infer body shapes from velocity points. The idea is that you give me some points in the flow field and you tell me which body produced this data, and I'm able to infer for you with the accuracy that I'm showing here what is the body and compared to the original description. There is a multi-resolution version of ODIL. The idea is that you use a hierarchy of grids to write this optimization of the discrete loss. And then, similar to multi-grid, you can have interpolation operators. We keep using automatic differentiation in the different grids. And again, here is a comparison of pins versus ODIL and MODIL for solving the lead-driven cavity at Reynolds number of 100. This is the vorticity, the reference, and ODIL. You can see quite good accuracy. This is pins and the reference, and you can see the amount of epochs that I need in order to do the training. I have about 3 orders of magnitude better in the number of epochs that I'm using to get the result to a factor of 10 to the minus 6. Yeah, you can find more details in these papers. They're still on archive. We're still trying to publish them. Either they tell us we don't use the pins very well, or all this thing has been done before. But that's life these days. So I'd like to continue and close with scientific multi-agent reinforcement learning. This is alloy number 3. So first of all, what is reinforcement learning and why do we care about that? So reinforcement learning, first of all, it's in the domain of psychology, behavioral changes of an animal due to certain experiences. You have actions that you take, there's a stimulus, and then you get a reward. Many of you probably know about Pavlov's dog to understand this conditioning that was going on. So reinforcement learning, and it's actually this conditioning where the stimulus action pattern is rewarded. That's an important thing. Then the actor is conditioned to this behavior. The dog is salivating every time it hears the bell because usually it gets rewarded with food. So in the field of animals and psychology, some of that stuff started at Harvard back in the early 50s by a guy called Bruce Skinner, who was training pigeons. I'm sorry.
The 2 pigeons are at the end of a small ping pong table. One pigeon sucks the ball as it comes toward him and knocks it toward the other pigeon. The other pigeon tucks the ball back across the table. If it goes past one pigeon, the other pigeon can eat, and if it goes the other way, the other pigeon eats. So it's a real game. The pigeon.
So you see here, every time that someone scores, they get to eat, and then the idea is that these pigeons are conditioned. So I don't know if you know the story of this pigeon or what was the application that Bruce Skinner had in mind. It's quite interesting. You can read all about it in this article by the MIT Review. Basically, the idea was that you use the pigeons as pilots inside missiles. You put the pigeon inside the missile. Whenever the pigeon sees a particular landscape, it pecks on a button expecting food. Instead, the missile goes down. And here's Bruce Skinner, who had these ideas, and he did some very interesting work. Actually, he published something called the misbehavior of organisms, which is quite interesting works. Now, reinforcement learning has received a lot of attention over the years. You can see it in all sorts of different games. Let's look at its behavior. So what does it do? How can you formulate it? You have an environment. You observe the environment. You get some states. You take some actions. The environment also gives you some kind of a reward. And now you have actions and states, and you have a policy. As we call it, this is a probability distribution. So you're trying to accumulate reward over a long term. So what you're doing here is you're trying to maximize an expectation over a particular policy. The policy has weights. So one way to create these policies is by making a recurrent neural network that receives states and then produces mean and covariances for a Gaussian probability distribution. You sample this probability distribution, you take an action, you compute your expectation according to this probability distribution, and now you go back and change the weights of this recurrent neural network so as to maximize the reward that you have. It's an interesting method that is iterative, and it's interesting because you can collect all sorts of experiences. You can play the game many, many times, and now the question is, from all these different past experiences that I have, if I'm presented with a new problem, which one of the experiences am I supposed to use? In the reinforcement learning jargon, this is called experience replay. Actually, if you look a little bit closer to experience replay, you realize it's nothing more than importance sampling. You are about to sample from a probability distribution. Instead, you sample from another one. So if you look at it like that, then you can think of adding a few constraints on the probability distributions that you are using. So we came up with this concept of remember and forget experience replay, where you are rejecting samples when the importance weights are outside the trust region. And also we penalize the reward based on a KL divergence between the two things, the two probability distributions, the online and the offline probability distribution, so that you attract the policy back towards training behaviors. We compare with some of the best reinforcement learning techniques and some benchmarks on reinforcement learning. There's the humanoid, that basically a set of ODIs, and the idea is to find out which one can go furthest over a certain amount of time. Obviously, from these pictures, you cannot see anything useful, but if you look at the comparisons we have done with state-of-the-art methods in terms of the reward, we find that this remember and forget experience replay seems to be operating quite well for quite some time. And the other thing we found is when we try to do fluid mechanics problems, often off-the-shelf reinforcement learning algorithms were not very easy to interpret. You can see actually that the Kullback-Leibler divergence of this is actually going down in our cases, but for the other algorithms, when we compute it, it kind of stays straight and is not converging. We think this is why this remember-forget produces good results. So we have played with this reinforcement learning for about 10 years now, and we have been studying fish swimming, collective hydrodynamics. There is all sorts of theories of how fish should be arranged in order to extract benefit from each other wakes, and also there's also interesting things. Yes, the fish do that. What can we learn from that? And can we design better arrangements for wind turbines? You can see here the power output of wind turbines that are on the wake of each other is quite uneven. Can you learn from that to design arrangements for that? So let's look at two fish first. So here's two fish. You see that they have a particularly interesting arrangement of siding with each other. So we do simulations. First of all, two-dimensional simulations. We have a fish that is swimming, producing vorticity, a fish that follows, that can change its curvature. It observes the location of the other fish. It observes its own motions. The states is a big thing, and then it gets some reward. So the first thing that we did is, can you swim right behind another fish? Can you learn to do that so you don't get pushed away by the vortices? Well, you can do that. And so the follower here, it learns to swim right behind the other fish. So even though we found that it swims inside the vorticity field, the power of deformation of the follower is less than the power of deformation of the leader. And what we found actually, that it is efficient to swim right there. Even though we didn't optimize for that, we got an extra benefit of about 12%. So the next thing is, can I optimize for efficiency? Now this fish here can swim anywhere. This fish here swims in a certain line, and these are early stages of learning. And you can see actually that the fish up there it would slowly realize that there is another fish down there, and it will go and start to swim inside the web. This is early stages of this reinforcement learning process. You can learn a few things from that, and then at the later stages we find actually some beautiful fluid mechanics. Without reinforcement learning, I think I would not be able to figure out this fluid mechanics. What we find is that the fish anticipates with its head the oncoming vortices. It tries to synchronize with their rotation and the turning of its head, and then we get an efficiency of about 28%. We take these lessons and we do three-dimensional flows, where actually we teach the fish now to harness vortices in 3 dimensions by swimming a little bit offset, because right behind the other fish there is no vortices. For this particular tails, the vortices are moving sideways, the vortex rings, and you can actually get and extract energy even if you are in situations like this ones, in particular the top one, where you have one fish following 2 other fish and harnessing each one of the vortex rings that are coming on each cycle is quite an interesting thing for me. We're doing some big calculations where we're having now 300 fish. This is simulations that involve adaptive mesh refinement, close to 1 trillion of computational elements, supercomputers, and so on. We are interested to see if we can actually extract knowledge from this collective hydrodynamics. So this is work that maybe I can talk more about it sometime in the future. There is also things we do on training drones and navigating in different flow fields with a group of John Dabiri at Caltech. We have also some structures that are going now and trying to attack certain tumors inside small capillaries. This is an artificial bacteria flagella reinforcement learning applied to their rotation. And I'll conclude with how you can actually take these ideas from control and use them to do closures. So if you have, again, we return to equations. And now if I have an equation, any PDE, Navier-Stokes, whatever you want, and I decide that I'm able to resolve some of its scales with U bar, and then there is a U prime that I cannot resolve, then if I do the substitutions, I may get a form like that. And then what people have been doing is they have been doing ingenious and beautiful models to try to use the mean field quantities to capture these other quantities over here. So my idea was, how about if we do reinforcement learning to capture, to learn these mean field quantities. So it almost looks like a problem of control, if you like. Now, the problem is that if you want to do reinforcement learning, even in a modest LES grid, you have a huge problem. Because a modest LES grid, let's say is 32 cube, that gives you about 10,000 states. It gives you about 10,000 actions that you have to take. And so that's problem impossible. So then we thought of the following thing. We thought that what are the numerical schemes do? The numerical schemes, they take information from grid points and they come up with a function to combine the grid points to advance the solution. So you can get this F from numerics, but also perhaps you can get this F through reinforcement learning. So now the computational elements can have a dual role. They can be both discretization points and learning agents. And this is the idea of multi-agent reinforcement learning. So now I can use my grid not only to solve the equations, but also to learn quantities of interest. So the nice thing about this is that you can naturally account for compounding errors. You can learn pattern by actually plugging in the model and learning through intervention. You learn to reproduce quantities of interest. You are not interested to reproduce the whole flow field, but it has the benefit of using limited data. You don't need to know the whole flow field. The reward can be something that an experimentalist can give you, or maybe some energy from a DNS. So we published this a couple of years back. So we first tried homogeneous turbulent flow. We tried to learn the Smagorinsky coefficient in a usual Smagorinsky type of model. The states that we used was quite an interesting exercise. I can come back to that if you like. I want to show you the results. We tried different policies. Let me guide you through these plots. The black lines are DNS of the energy. We tried different Reynolds number, and then we trained on these Reynolds numbers, and we tried to interpolate and eventually extrapolate to 190 and 205. The purple is what you get by standard Smagorinsky, and the green is dynamic Smagorinsky. The blue policy has been trained in all these Reynolds numbers, and it seems to be doing quite well throughout. This is the error. It seems to have the smaller error of all of them. The yellow is also an interesting policy because we trained it only to reproduce the results at Reynolds number 111. And it's interesting that it produces good results at higher Reynolds numbers and a little bit less good results at lower Reynolds numbers. And we had policies that are based on the Germano identity that they fail. So the policy is quite a critical issue. We extended this also to wall-bounded flows. This is wall turbulence. What people do here is they're coming up with wall models. And for these wall models, you have to provide the kappa and the B. And when you provide the kappa and the B, then you can use this wall model. The problem is the kappa and the B, they change with different pressure gradients. So what we try to do is we try to create estimates of this kappa and the B. So we did reinforcement learning again, where we have an action, which is simply a very small adjustment of the shear that we put in the outer layer of the place where we apply the law of the wall. And we use as states these two expressions that if you pay attention to them, they're actually estimates of the kappa and the B, but without knowing the kappa and the B. These are all quantities that we have from our simulations at these off-wall locations. They come from the LES themselves. The results are quite interesting. We train up to RE tau of 10 to the 4 for a channel flow. And then when we do the right states that I showed you, you get extrapolation up to RE tau of 10 to the 6. So it starts to become really interesting. And also by training only on channel flow, then we can take it to an evolving turbulent boundary layer without training. Of course, you can tell me the boundary layer is similar to channel flow, and I totally agree. But nevertheless, we got a quite good generalization for quite some Reynolds numbers. I'd like to conclude. I'll be happy to, I will not give you a summary. I hope you can make judgment of all the different things, and I'll be happy to take any questions that you may have for any of these topics if interested. Yeah. The novelty of ODIL is just to demonstrate you that you can do orders of magnitude better than PIN. It's a fair comparison, I believe, between classical methods and PINs. And the other novelty is that we are using automatic differentiation. We're using multi-resolution ideas to run this cost function over different grids, and that we are actually using data in the same way as PINs do. There is So all I want to say is that you can be orders of magnitude better than pins by doing these other discretizations. In 90%, what you say is true. People have not done automatic differentiation before. People have not done multi-resolution on the different discretizations as we do now with this ODIL. Yes. Continual learning is actually what we do now with many of these RNN LSTMs. I totally agree. You don't need to start from scratch. So continual learning is something that we are actually pursuing at the moment. Yeah. Yeah. Yeah, so what we try to do is we try to incorporate some form of uncertainty quantification in our predictions. And for that, the direction that we take is the direction of conformal inference in order to provide some kind of bounds for the predictions that we get out of our machine-learned models. I understand that we are probably abusing the theoretical foundations of conformal inference to try to do this with machine-learned models, but that's actually one direction we try to take. We try to create uncertainty for our predictions based on that. Of course, you can do Bayesian inference also, but that's a little bit more complicated for me. Okay. Thank you. Have a great day.